My name is Shreya Jairam, and this is my Physics 2211 Lab 4 about oscillations. So introduction, the purpose of this lab is to track the oscillations of a spring in 2 dimensions and to create a computational model to demonstrate it. The fundamental principles used in this lab include Newton's second law, depicted as Vf is equal to Vi plus F net over m delta T, as well as the energy principle, which is E is equal to K plus Us plus Ug, and the equations for kinetic energy, spring potential energy, and gravitational energy. The results of this lab show that the computational model predicts the motion of the experimental spring almost exactly with only small errors. So the models. So as stated before, we're using Newton's second law, which is velocity final is equal to initial velocity plus F net over m times delta T. And then the energy principle is total energy is equal to kinetic energy plus spring potential energy plus gravitational potential energy. And then we have kinetic energy, which is 1/2 mv final squared minus 1/2 v initial squared. And then gravitational potential energy is mgh, and then spring potential energy is 1/2 ks squared, where s is the length minus the relaxed length. So experiment. The initial conditions from tracker were a time of 0 seconds, a position of negative 0.118 meters, and a y position of negative 0.629 meters. The system is the ball, the spring, and the earth, and the surroundings include everything else in the universe. And then the 2 graphs plotted by tracker show x position versus time and y position versus time. So as we can see here in the video, as the video plays, we have tracker tracking the positions of the spring for the first 5.5 seconds. So code. The mass, the spring constant, and the initial length were givens. As we can see here, I have that right here. And then the position vector I got from the first tracked points in tracker. And then I calculated the velocity vector by taking the velocity of the first 2 points from the data that we collected. And then, of course, we have G, which is a given again, which is a gravitational constant. And then we have Ks is 6.83, and then the initial length was 0.123, and both of those were from the pre-lecture 52 video. And then lines 89 through 91 solve for the change in length used for the spring force calculation, as you can see right here. And then lines 94 through 97 initialize the energy before the experiment starts. So these are just the equations for energy. And then lines 110 to 113 define the initial energy of the experiment before it is released from rest. And then lines 16 is the model for the force of gravity. Line 119 is the model for the spring force, and then 122 is the model for net force. And then lines 126 to 128 are position and velocity updates, and then 131 to 133 update the length of the spring in that moment in each time frame, and then 139 to 146 calculate the change in energy, which will be used to plot later. So discussion. As shown in the graphs to the right, the predicted positions from the model closely resemble that of the observed data. In the x direction, the positions are almost identical, and in the y direction, the model is very close, except at the crests and troughs. This can be due to error in tracking manually, or because a minimal drag force or some other force that was not accounted for was acting on the spring. So what does it mean? As shown in the graph, the computational model I created shows that energy is conserved in the system. The change in energy stays at 0, and Ug as well as U spring oscillate almost perfectly. The kinetic energy dissipates eventually, but that could be due to outside forces acting on this system which were not accounted for. The period of oscillation for this x direction can be estimated to about 1.614 seconds from tracker, and the period for the y direction is estimated to be about 1.519 seconds. The difference in periods can be due to the fact that there is gravity acting on the spring in the y direction as well as the spring force, but in the x direction there is only spring force. Conclusion. In conclusion, I created a computational model that demonstrates Newton's second law, the energy principle, as well as models of spring force, gravitational force, and kinetic energy. The model I created also closely resembles the experimental data.